the eye, quite a bit into the eye, and how the eye works and the optics of the eye. We talked about electromagnetic radiation, how this is caused by moving electrons. In fact, if you're into radio transmission or radio receiving, you have that big long metal antenna. All that's happening is you have an electron moving up and down, up and down, up and down, and it's sending out electromagnetic waves at a particular frequency. The frequency of light gives its a color of it. We talked about the speed of light, various other properties, all the same properties that we had talked about, excuse me, properties that we had talked about before, wavelength and frequency and speed. They're still related here in the same way as they were for sound. That is to say that the speed of light, v, is equal to lambda frequency, or we call our speed of light this value c, because it has like this maximum limit, and we call that a constant value, though we'll see that the speed of light actually changes when it goes into different media. So it doesn't mean that it's constant necessarily. The speed of light does change. It just means it has this maximum value. All right. Talked about the electromagnetic spectrum. You need to know that spectrum and its order: gamma ray, X-ray, ultraviolet, visible. In the visible, you have, gosh, what is this? It's Roy G. Biv going the other way, but here it's VibGyor. Infrared, microwave, and radio. Know those in terms of energy, frequency, and wavelength. Energy and frequency are in the same direction because they're directly correlated to one another. Big frequency, big energy. Big frequency, short wavelength. Okay, so like gamma rays, very, very short wavelength. In fact, we don't usually talk about the wavelength of gamma rays. Radio waves, very, very small very small frequency, but long wavelength. Like radio waves can be a meter long, they can be 10 meters long, they can be as big as our planet. Radio waves can be very large. All right, we did all these? No. Okay, well, let's do this top left one. Light is a what with both what and what? All right. Let's stop at 50. Get your clickers out. 50. Okay, good. A is right. It's a wave. It has frequency and wavelength properties. It's not any of those other things, although if you read about light, you'll find that in the history of light, that it actually, people have thought that it's a particle in the history. And actually, we're not going to get into this, but light, depending on how you look at it, can look like a particle. Can look like a particle. Don't write that down because we're really only dealing with the wave-like properties of light. So A is the right answer here, and that's how we'll consider it, that it is a wave with both frequency and wavelength. Hey, do you know why you can never, ever starve in the desert? Because of all the sandwiches there. Let's do this one on the right. Which of these has the highest energy? Blue, ultraviolet, radios, or gamma rays? About 10 more seconds. Stop at 25. Okay, gamma rays. A lot of you put ultraviolet light, and among visible, ultraviolet does, or excuse me, no, it's not even visible. No, gamma rays have the highest energy. That's why gamma rays, you need to really limit your exposure to them, severely limit your exposure, because they can actually kill cells in your body. All right. So radiation treatments, for example, often use gamma rays. and those will kill the cells in your body, and that's why it's so damaging to you in the treatment of cancer. But that's also why it works to treat cancer. Yeah, Stefan? Yeah, this is high energy on the left, low energy on the right. It is small wavelength on the left, long wavelength or big wavelength on the right. All right. Which of these is the proper order from smallest to biggest energy? Gamma, infrared, microwaves, ultraviolet. All right, let's stop at 45. 45. Very good. A is, or B is right, rather. Microwaves, infrared, ultraviolet, and gamma rays. Just know your electromagnetic spectrum. Know how to order those things. And then the energy of a wave is dependent on which of these? Is the energy dependent on the speed, frequency, amplitude, or is it on the medium? We're going to begin to see a little shift because we thought about these waves differently before. Okay, good. You're doing great. Please share your answer with your neighbor if you like. If they're uncertain, because most of you have the right answer. All right, let's stop at 35. 35. Okay, good. B is right. The energy is dependent upon the frequency. Let's see, somebody put speed. Now, the speed is dependent upon the medium. So the speed doesn't really have anything to do with the energy of the wave, but the energy is dependent upon the frequency. Let's see, why does a gingerbread man not like to wear shorts? Because he has crummy legs. Okay, let's look at visible light. Visible light, as we saw, is just a tiny little part of the spectrum of electromagnetic radiation. Um, it is, but it's still part of the electromagnetic spectrum. We use this Roy G. Biv for our spectrum. That's our visible light spectrum. We can see them in that order: red, orange, yellow, green, blue, indigo, and violet. And visible light is caused by electrons moving in or out of energy states. We'll see this next chapter when we do nuclear. Oh, we may or may not. We'll talk about the model of the atom. So in an atom, you have protons and neutrons here, and then you have these shells, these orbital levels. And an electron can move from one shell to another. So it can move down in this way, and if it does that, it emits a photon. It emits a little bit of light. And depending upon the energy difference between those shells, it'll emit a photon of a particular color or a particular frequency. The frequency is dependent upon the color. So frequency is dependent upon the color. Likewise, energy is dependent upon the color. Which light has more energy, blue light or red light? What do you think? Blue light or red light has more energy? Blue light has more energy. That's why in a fire, what's the hottest part of the fire? The blue part, right? The orange stuff that's up top, that's just like window dressing. It's down in the middle of the fire where you get those nice blue flames. That's the hottest part. I mean, that's not where you want to put your marshmallow, right? You don't put your marshmallow in the flames anyway. You just sort of hold it up above the fire, and the infrared radiation from the fire comes up and toasts it, make it all melty and gooey on the inside. The energy range for visible light is is about 1.8 to 3.1 electron volts. You don't need to know those numbers, but I want you to know that there is a range of energies for the Roy G. Biv spectrum. So this is 1.8 electron volts down to 3.1 electron volt. An electron volt is an energy. It's a charge times a voltage. Remember we said that voltage is energy per charge. So if I multiply it times the charge of an electron, then I'll get a certain amount of energy. It describes the difference between these energy states. I get so many electron volts. Let's say this is like 1.8 eV. And if I have a difference in energy of 1.8 eV, then it's going to emit a red photon. If I have a bigger energy difference, it's going to emit a blue or a violet photon. This is the range of energy required to move or remove electrons from many molecules and atoms. To move those electrons in between those energy states of an atom or a molecule, and it produces different colors. So I mean, you know, Alexa, look at your red jacket. It's a nice, pretty red color. The reason that it's red is because there are electrons, as light shines upon it, there are electrons that are moving back and forth, and they're emitting these photons that are red. That's the process of producing color, that I have these electrons that are moving back and forth between these energy states. You ought to know that, did you? Yeah. All right. Let's see. You ever seen a rainbow? Too cloudy out there to see one today, but we might see one later in the day. Purple in a rainbow? Yes or no? What do y'all think? You ever seen purple in a rainbow? Did we already talk about this? All right. Did I show y'all the video too? Did you go tell your friends? Isn't that interesting? There's no purple in a rainbow. Man, I was about to dazzle y'all with information that you did not know. All right. So waves and rays. Wave fronts. I'll define what this is. Emanate outward from a source of light at the speed of light. That's that speed c that we talked before. And so, like, for example, if I have a point source right here, it's like a light bulb or a star or whatever, there's light rays that are emanating outward in all directions from that. Now, um, if I have a source I'm very far away from it, so the rays become parallel. So rays are parallel at a large distance from the source. So you see right here, I have these rays coming out, and then likewise over here. They're not parallel, right? They're sort of moving apart from one another. Right here especially, I can see that these lines, they're diverging. But if I move a very, very far distance away from the source, a really far distance away, by the time those light rays get to me, they're basically parallel. Because like, for example, with the sun, I'm only seeing a portion of the light rays from just, you know, a small part of the sun. And down here close into the sun, or whatever my light source is, the close together rays, those are approximately parallel. So if I have a light source, it's emitting light rays in all directions, but if I move far away from that light source, I can imagine that the light rays are parallel. You don't have to be that far away from a source for the light rays to be parallel. You can be just, say, 100 feet or maybe even 10 feet, depending on the size of the source. When we consider rays of when we consider rays of light, we draw light as shoot, I'm sorry, I didn't know what I had here. Sorry, folks. I want to tell you about the wave front. So when we consider rays of light, we draw light as lines perpendicular to the wavefront. I'll explain it in the picture a little bit better. So I have these light rays. I imagine this line in front of the light rays, and that's what I call the wavefront. You'll see how this is important a little bit later. I can imagine a ray picture of light, and that's just like where I have a single ray of light that's traveling. But really when I have light that's traveling, I have many rays of light that are traveling together, kind of like, I don't know, a phalanx of soldiers, right, that are all marching together in the same line. And so we're going to think about this wave picture of light as a wavefront that's going through space. And it has a certain width and a certain depth as it travels through space. You'll see why this is important later when we get into refraction. But this wavefront will be important in sort of how we think about light traveling. So we'll use the wave picture in discussing refraction. That is how light bends and how it slows down. And the ray picture in discussing reflection. All right, so this is the wavefront picture, the wave picture of light. And then if I'm talking about just like a single ray, this would be like the ray picture of light, or the way that we think about light as a ray and not as a front of waves. Two different ways of thinking about light. This wavefront thing, which is a collection of rays, and then also just as a single ray. You'll see why that's important in just a moment when we get to refraction. All right, so a good portion of this chapter is on geometrical optics. We'll look at lenses and how we use lenses to correct for things like near and farsightedness. But all these depend upon refraction. And refraction is a phenomenon for waves. The waves travel at a different speed in different media. We saw this for sound. Do you remember with sound? We saw that sound travels at different speeds in different media. Like, for example, it travels faster in water than it does in air. That's why the whole shark thing, we watched the shark video with the triangulation. You watched that? Didn't we? Where you close your eyes and you listen for the sound? With that girl, yes. We did watch it. No, we did. All right. Um, but anyway, it's similar to that, that waves travel at different speeds when they enter different media. We give this by the index of refraction, and n is equal to c divided by v, where n is the index of refraction, c is the speed of light. We've already given that. It has a value of 3 times 10 to the 8th meters per second in a vacuum. In other media, it has a different speed, slightly different speed. And then v here, this is the speed in your particular medium, which is described by that index of refraction. For a vacuum, well, what is n for a vacuum? If c is the speed of light in a vacuum and v is the speed of light in the medium that you're concerned with, what is n for a vacuum? What must n be for a vacuum? Well, the speed of light is c, and v is the speed of light in that particular medium. So what must the speed of light in a medium be if the medium is really a vacuum? What is it? You're about to say it, Caroline? No, you're about to say it. Well, guess. No, that's a good guess. What is the speed of light in a vacuum? What's the speed of light in a vacuum? Come on, no, we just said it. It's right up there. What's the speed of 3 times 10 to the 8th? Right, so that would be v, and then c is also 3 times 10 to the 8th. So what must n be for a vacuum? It's what? It's 1, right, because it's 3 times 10 to the 8th over 3 times 10 to the 8th. So for a vacuum, n equals 1, and for all other media, is n smaller than 1 or bigger than 1? When light enters other media, does it speed up or slow down? Does what? No, it slows down. When light enters, say, glass or water or any other medium, it's going to slow down. So is n going to be smaller than 1 or bigger than 1? It's going to be bigger than 1. So our index of refraction is always bigger than or equal to 1. It's equal to 1 if we're a medium, in a medium. And actually, we'll talk about the index of refraction for air being the same as for a medium. And it's pretty darn close. It's a little bit different, but it's really close. All right. Traveling at different speeds as it goes to different media can cause the light to bend. So imagine that I have a front of waves. Right? They have a wave front here, and they're all going in this direction. Now, when they enter into this medium, say I'm going from air into, say, I don't know, glass. So I have air on this side. I have glass on this side. For air, n is equal to 1. For glass, n is about 1.5. So, for example, if I wanted to know the speed of light in glass, I would say that it's v equals c divided by n. That's 3 times 10 to the 8th divided by 1.5. 3 over 1.5, what's that? That's 2 times 10 to the 8th meters per second. So when light's traveling on this side, it's traveling at 3 times 10 to the 8th meters per second. When it's traveling at this side, it's traveling at 2 times 10 to the 8th meters per second. What's that? 200 million meters per second. 300 million, 200 million. It slows down considerably, right? By 100 million meters per second. That's a lot. So what happens when this thing enters this medium? Well, this side is going to slow down, but this side of the wavefront is going to keep going faster. So which way is it going to turn? Is this thing going to come down here, and is it going to go like this and travel in that direction? Or is it going to come down here, and is it going to bend in that direction? Which way is it going to bend? Is it going to bend, what's that, to your right or to your left? Away from what we call the normal line or towards the normal line? Which way do you think it's going to bend? That way or this way? That way or this way? Okay, I see both. People are doing both. Uh, you ever drive I don't know, a tank? You ever drive a tank? Or have you driven a tank? You haven't? Okay. She's like military family. I thought she might have. How about a bulldozer? You driven a bulldozer? Yeah, I've driven a bulldozer. You have tracks on a bulldozer, right? And if you want to go, say, that direction, you make this track go faster. And then that's why you have two levers, I think. I've never driven a bulldozer, but my understanding of them, that's how they work. Or if you've ever driven a twin propeller boat, a boat that has two propellers on the back, it's the same idea. That if you want to turn that direction, you make this propeller go faster, and it shifts you over in that direction. Or you make this propeller go faster, and it shifts you in that direction. Or you can make them go backwards, but that doesn't fit here. Or y'all in the marching band? This is sort of the typical analogy that people give. In the marching band? Just me? Come on. I'm not the only dork in there, am I? Thank you, Derek. What'd you play? French horn. I played tuba, so we're both pretty dorky. All right, so in a marching band, you all travel together. But if you go from, say, asphalt, where you travel fast, to a muddy field where you travel slower, imagine traveling along. This side slows down, and this side keeps traveling fast. And so like the marching band, or like the tank, or like the twin propeller boat, or whatever, the bulldozer, you're going to move along here. This side will slow down, and this side will move on faster. And so your wave front will move in this way. It's going to sort of bend, 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 and then when it gets into the medium, it'll travel along at the same rate. So when I move from a low index to a high index, I bend towards what we call the normal line, which is this line. Let me redraw this without our wavefront now. I just draw it with a ray. I have a ray coming in like that, and it's going to bend in that direction. This is moving from n equal 1 for air to n equal 1.5 for glass. Notice the index of refraction, by the way, has no units. It's a ratio of speeds, and so the units all cancel out. All right? So the way I measure these angles, always in optics, I measure my angle here, and I measure my angle here. This is theta 2. This line we call the normal line. Not because it's usual or typical, but normal is a mathematical term. Anybody know what normal means in math? It means perpendicular, or at 90 degrees, so they're perpendicular like a T. And so this dashed line is the normal line. It's perpendicular. So we'll always measure our angles in optics from a line that's perpendicular to the surface. We'll do some practice problems so you can practice. You need to know how to figure out which way does light bend for these different surfaces. It's very important for the eye when you're fitting lenses for the eye to help correct the direction that the light rays travel, that you know which direction those light rays will bend. These things are governed by the law of refraction. You're not going to have any problems with the law of refraction, but I want you to just see it. It's n1 sine theta 1 equals n2 sine theta 2. And so you can calculate those angles, and that's what people who design eyeglasses and other optical systems, they can calculate what is the angle that the light is refracted or the angle that the light is bent. You're not going to have to use the law of refraction to calculate things, but I just want you to know that it exists. Let's see. Have questions on the next page? Yeah, let's try some of these. So here, I have light moving from glass to water. I give you the indices of refraction. I want to know, does it bend towards the normal, away from the normal? Maybe it just travels straight through without bending at all, or maybe it reflects off of the surface of the water. Does it bend towards, away, travel straight, or reflect off of the water? I'm going to take this away for just a second. I will bring it right back. All right. Let's stop at 105. Just 5 more seconds. Feel free to ask your neighbor what they put, okay? 105. Okay, B is right, I think. Let's see. So I always have to think about these. Don't try to memorize them. It's easier just to sort of think about these analogies. Here's my light rays coming in. I'm moving from an area of high index, that means low speed, to high speed. So I'm going to speed up when I go into this new medium. And so these light rays come along, these wave fronts, they're going to speed up right here. That's going to cause the thing to shift off in this direction. So it's going to bend away from the normal. So you need to know the direction that they shift. You also need to know how to define the normal and what that means. Let's go down to this next one. It's a light bulb emitting light in all directions. How am I considering this light? As parallel waves, rays, circular path, or as wave fronts?